Welcome to Summarize Science. The TRAPPIST-1 system, with its 7 Earth-sized planets, has long been a top candidate in the search for life beyond our solar system. But a critical question has always loomed. Were these planets born wet, with oceans and atmospheres, or were they born as dry, barren rocks? Getting water to planets so close to their star is tricky. The methods we think worked in our own solar system, like giant planets flinging icy asteroids around, probably didn't happen in compact systems like this one. To find an answer, a team of researchers built a sophisticated computer model to simulate the birth of TRAPPIST-1-like systems. This wasn't just about planets growing. It was about tracking the fate of essential ingredients like water and carbon through millions of years of violent collisions. Their model, shown schematically here, is like a cosmic accounting system. It tracks these vital compounds from the initial disk of dust and gas into the final planets, accounting for losses from impacts and the star's radiation. The results, visualized in this plot, reveal a dramatic and consistent pattern. In almost every simulation, the innermost planets, like TRAPPIST-1b and c, ended up with very little water, sometimes less than 1,000th of Earth's oceans. Their close proximity to the star meant they experienced more frequent, high-energy impacts that blasted away any atmosphere they tried to form. But as you move further out, the story changes completely. The simulations show the outer planets, like F, G, and H, were much more successful at gathering and holding onto their water, frequently ending up with inventories similar to Earth's. This finding provides a powerful, physics-based explanation for why the James Webb Space Telescope has failed to detect atmospheres on TRAPPIST-1b and c. It suggests they weren't stripped away over time. They may have never had much to begin with. The story gets even more extreme when the researchers factored in the star's youth. Young stars go through a prolonged, incredibly bright phase, and when this was included, it effectively dried out the building blocks of the inner planets before they even formed. You can see the difference clearly in these histograms, where the gold bars representing this early bright phase show a dramatically drier outcome for the planets. So, what does this all mean? Let's recap the important points. First, the way a planet is built through countless chaotic impacts is the primary factor in determining its initial water budget. Second, in compact systems, location is everything. Being close to the star is a recipe for a dry world, while the outer orbits are a much better place to find water. And third, the intense brightness of a star in its youth can deplete the inner parts of its planetary system of water from the very beginning. For the future, this research provides a crucial guide for astronomers. It suggests that if we're looking for habitable, water-rich worlds in systems like TRAPPIST-1, our best bet is to focus our attention on the colder, more distant outer planets.